Okay, so let's continue. So if we look at the response of a linear time invariant system, we can um, calculate it by multiplying the transfer function in Laplace transform of the input signal. So h of s times u of s. Now let's assume the transfer function is possible to rewrite them in this form. So this is our transfer function. So in other words, all the lambdas here are still the characteristic roots. They are the characteristic roots. And z1, z2 of the zm's, they are called the zeros of the transfer functions. The lambdas are also called the poles of the transfer functions. And since there could be a constant or a leading coefficient, usually in the numerator, so we have this additional b m to represent, well, this is the coefficient of the highest order in the polynomial of the numerator in the transfer function. So this is the transfer function. Also, let's say it's possible to rewrite u of s, the input signal's Laplace transform, in a similar, but we'll do it relatively simple. Let's say they are p1, p2, and there may be, let's say, q of them. Okay, q of them. And there may be some terms on top from the input signal as well. So this is your u of s. Okay. And as we all know, right, when you use this formula, this is actually the zero state response. All the initial conditions are zero. And this is what we're going to focus on. Now, we all know also, when you have this form, especially when you can separate all the poles from the transfer function, all the poles from your input signals Laplace transform, we can apply the partial fraction expansion method, right? So it's possible to write this as the partial fraction form of all the roots. So there will be a total of n of them. Right? And all these L's can be obtained, for instance, using the cover-up methods, okay, if there are no repeated roots. Okay? And also, since you have this s minus p1, p2 terms, there will be other terms involved that corresponds to the poles of your input signal, like this. Now this is the partial fraction expansion of y of s. And now if you apply the inverse Laplace transform, what will you have? So now we have our building block signals, right? So when we continue, we're going to have y of t, and the inverse Laplace transform, the first term will be L1 times e to the lambda 1t plus L2 e to the lambda 2t. Okay. Like, what do you have done in ECE 3101? When we do the partial fraction expansion, this is what we have. And then for the other terms, we'll have k1 d to the p1t and to the last term. Okay. So basically, for a linear time invariant system, the response will be a combination of exponential signals. Okay. And if you think a little bit further, okay, think about what we have discussed in 3101, these terms have all the roots or all the exponents being the characteristic roots. And all of these guys, we give them a special name, right? We call them the natural response. Because all these exponential signals are defined by the system itself, by the transfer function itself, by the characteristic polynomial, characteristic roots themselves. They are naturally possessed by the system, by the linear time invariant system. So that's what we call the natural response. And of course, the other ones, we call them the forced response. Since these exponential functions are defined by, as we can see, the poles from the input signal. So all these p's come from the input signals. They're defined by the external input signal. Now, so that's why we call them the forced response. And in most cases, the forced response will look very similar, will take very similar form, or usually resemble the input signal itself. They'll look like the input signal. Now, keep in mind that we only focus on the unit step response. So for unit step response, the natural response should still take the same form as before, still these exponential signals. But the forced response will be special. The forced response, again, as I mentioned, should resemble your input signal, since your input is a unit step. And if we only look at t positive, meaning after the switch on this unit step signal, basically the input will be a constant, and the forced response actually will be a constant. Now, of course, we can say this is because also that we assume the system is asymptotically stable. So, asymptotically stable systems, this is possible. And if the system is asymptotically stable, then all the e to the lambda it's will eventually decay to 0 as t goes to infinity. Okay? This is the result of an asymptotically stable system. All your natural response will decay to 0. So all natural response will decay to 0 when t approaches infinity. So after a sufficient long period of time, when you observe the system response, you can see nothing that carries this characteristic roots of the system, and everything you see will be the result, or will resemble the input signal. Now, if that's the case, and if we go back and look at this function, if all the lambda terms go to 0, so if this one goes to 0, this one goes to 0, these ones goes to 0, that means in the steady state, when sufficient long period of time has passed, the value of the signal will be equal to k. Right? What does it mean? It means, well, I enter a unit step into an LTI system. It's asymptotically stable apparently. And at the output end, if I make the observation after this, okay, what I do know is after sufficient long period of time, the signal will carries this value k. Now what happens in the middle is not known particularly. It can move like this. You may go into the steady state like this, or may take some other shapes. But what I do know is in the steady state, when a sufficient long time has passed, okay, you basically read this value k if you can measure the output. Then in 3101, how do we call this? Okay, the input has magnitude or amplitude, signal character, the amplitude is 1. The output in the steady state will be k, and when T is positive since the input is a constant, it's like a DC current or DC signal. So at the output in the steady state, this input 1 becomes output k, so it's amplified k times. And this is what we call the DC gain of the linear time invariant system. And the DC gain can be calculated, if you still remember this from 3101, is your transfer function h evaluated by replacing all your s terms in the transfer function with 0. And that will be DC gain. So if you enter a DC signal into your system, after a sufficient period of time, you will also see just a DC signal at the output in the steady state, and the amplitude is k times the amplitude of our input. That's what we call a DC gain. Now, this is what happens in the steady state, but as I mentioned, we're also interested in what's going to happen in the middle. We're also interested in this part. And there are qualitative measures and there are quantitative measures of the transient, meaning within this period of time. Now, quantitatively, how can we evaluate the system performance? We'll discuss this in the next video.